Hello everyone, here we'll be discussing chapter 2.5, which is a section on continuity. And here I first say a function f of x is continuous at x equals a if the limit as x goes to a of f of x is f evaluated at a. In other words, DSP applies the direct substitution property, that is, applies directly to f at that particular limit value. Now, a better understanding of this from a graphing perspective is if you consider the graph f of x like this, and let's say this is the xy plane, and we have this x value a, and let's look at this point. It's continuous in the sense that there is no breaking in the curve about the point a. So it's continuous at a, meaning that to the right and to the left of that point, the function continues in a continuous sense, basically. There's no breaking point, basically. Now, a breaking point is what is called a discontinuity. So I say here a function is discontinuous at x equals a otherwise. So if it's not continuous, we call it discontinuous. Now, a discontinuous function, there's actually a few different ways you can view it, and we'll actually categorize those after this discussion here. But one we've seen kind of recently a little bit is when we had this piecewise defined function like this. We'll actually see shortly this is what is known as a removable discontinuity. And basically the graph is discontinuous here because it seems to move on smoothly up to this point, and then it jumps up here and then goes back down and continues. So if we were to cover this up, then it would be continuous, but the fact there's a hole there, there's a discontinuity at that point. Very similarly, if instead of continuing here, if it jumped over here, this is also a discontinuity in the graph. Because it's not just one smooth piece, there's breakage in the graph. And this is how we describe that, because notice, as you approach the a value, imagine this vertical point here is the x value x equals a. If you approach from the left or from the right, the limit is not equal to f of the value. In fact, f of a would be the solid point here. If they're both open, then f of a wouldn't even exist. But in this case, f of a is that. And notice, here the limit doesn't even exist because from the left and right, they're different. Whereas the image we had before, where it did continue afterwards from this open circle, well, the limit from the left and from the right would exist, but it's not equal to f of a because f of a is the solid bolt point. So I'm kind of digressing a little bit, but let's kind of move on to the matter at hand. So here we're discussing f of x equals x squared minus 4 over x plus 2. Now, you can kind of tell just by looking at it, there's a discontinuity at x equals negative 2. So let me just write discontinuous at x equals negative 2. Now, how I can tell right away is by setting the denominator equal to 0. And that's very often what you kind of look for. If you have a fraction function like this, or a rational function, you set the denominator equal to 0, and those results will be where your discontinuities lie. There are other scenarios where you may have discontinuities as well, but that's kind of the biggest eyesore as far as just looking at the expression anyways. Now, in this particular instance, we can actually graph this, and I'm going to show you something kind of funny happens. Let me erase this here. Now notice the top here actually factors, and we've seen something very similar to this in the past. This actually factors as a difference of squares, x minus 2 times x plus 2. And notice the denominator is x plus 2, so we get some cancellation. And notice all that's left over after canceling is just the expression x minus 2. Which is actually pretty good because x minus 2, we can actually graph, it's just a line. Its slope is 1 over 1, and its y-intercept is negative 2. Perfect. And let me just kind of a little more, right, perfect. So notice when you plug in negative 2 into this expression, you get negative 4. But if you plug in negative 2 into this original expression before canceling, well, you get, let's see, negative 2 squared is positive 4, minus 4 is 0 on top, and then negative 2 plus 2 is 0 on the bottom. 0 over 0 is not an actual number. We called that an indeterminate before. So in actuality, though this line is the graph of y equals x minus 2, This line with the open circle is f of x. So we have a discontinuity there. Perfect. So that's all I wanted to say as far as just getting introduced to the idea of continuous and discontinuous. And now we'll be actually looking at particular examples of discontinuities. And now, by the way, before we move on, this idea of continuous can be extended to a whole interval. So we can say that f of x is continuous at an interval if it is continuous for every x value in that interval. Similarly, you can discuss continuity from the left and from the right, but very often we look at continuity in a two-sided sense. So that's all I want to say there, and now we'll move on to actually discussing those categorizations of discontinuities. Alright, so as it turns out, there are three different types of discontinuities. There is removable, infinite, and jump. Removable I've kind of spoke about already, but basically we have a function that looks otherwise continuous except at one particular point we have an open circle. Now, of course, there may be many of these removable discontinuities, and at the same time, there may actually be a particular value for a that's not specifically filling this discontinuity. Now, of course, you can't have two of these for a because otherwise it would fail the vertical line test there and then not be a function. But anyways, the reason why it's called removable is because we can remove the discontinuity by redefining this function as itself, but then when x is equal to a, the value of the discontinuity, the y value of the discontinuity. So for instance, the previous problem we saw, x squared minus 4 all over x plus 2, this discontinuity was at x equals negative 2, and we saw that when we canceled things out, it just reduced to x plus 2. I'm sorry, it was x minus 2 what it reduced to. But in any event, if you were to redefine that function as a piecewise defined function, where when it's not equal to negative 2, you would have that function, but when it's equal to negative 2, you would just let it be negative 4 in that case. That would so-called fill in the removable discontinuity. So we're redefining it with a piecewise defined function, basically. But long story short, if it's an open circle, and you can just cover it up with a point, then it's a removable discontinuity from a graphing perspective. Infinite discontinuities you've actually also seen. This is where we have, for instance, y equals 1 over x squared. We have a vertical asymptote, and notice there is legitimately a discontinuity here because there's a breaking point. But it is an infinite type of discontinuity because instead of a particular point missing, there are no points missing. It's kind of piecewise continuous. There's no abrupt stop or anything, but there is definitely breakage in the function, in the curve of the function. There are two parts, here and here. A jump discontinuity is where you will have somewhat of an abrupt stop in the function, where it may do something like this, and then continue at a different y value point and carry on. And very often this happens with piecewise defined functions. Now you could have kind of instances that try to mimic combinations of these. So for instance, something like this, where on this side, there's a vertical asymptote and it would go up towards infinity. And that would be both an infinite and jump discontinuity. But in that case, I guess you would have to define things from the left and right. So from the right, it would be infinite, but from the left, it would be a jump, something like that. But in any event, let's move on to this example here, where we have this piecewise defined function, f of x is equal to these three things, depending on what x is equal to. And we want to classify the discontinuities of f of x. So to do this, I'll graph f of x by graphing each of these parts, and it won't be actually too bad. Let's see. Right, so the biggest thing we need to discuss are the x values, and notice there's 0 and 2 are kind of the breaking points where we jump from these one function to the next, basically. So let's consider x is equal to 0 and x is equal to 2. And kind of imagine this breaks the graph up into these three sections. Before 0, in between 0 and 2, and beyond 2. Now, before 0, when x is equal to or less than 0, we're using the function x squared minus 4, which actually looks like a parabola shifted down 4 units. So I hope I have enough space here. But that will look something like, let's see. Just to be specific, at 0 would be a negative 2. So it's a parabola like this, that's what it would look like. And I'm going to actually draw a closed circle here because it says or equal to 0, so meaning at 0, we're using this one here. When it's equal to 0, f of 0 would be 0 minus 4, which is negative 4. Good. Now, when x is in between 0 and 2, we're using x plus 2, which actually has a line as its graph. It starts at y equals 2 and then has a slope of 1 over 1. So it would go up like this. Let me kind of lift this up a little bit. So it would look something like that. The line would look something like that. Of course, this is not to scale, but that's kind of more or less how it would look. Now, I'm not going to continue it off beyond this red line I've drawn. In fact, I'm going to draw open circles here and here. And the reason being, of course, is because it is a not or equal to here. Okay, if it was or equal to, then we'd fill them in with solid circles. Okay, so now f of x is equal to 4 when x is bigger than 2. So f of x equals 4 is just the horizontal line like this, and that continues. And notice since it's not or equal to 2, I will not fill it in. So now let's kind of figure out what's going on here. So there's actually two discontinuities. If this was or equal to, or if this was or equal to, the fact that they both have the same y value at 2, notice 2 plus 2 for x plus 2 will be 4, and here when x is equal to 2, f of x is 4, of course. So if one of these were or equal to on the 2 side of things, then we'd actually have no discontinuity there. But since we do not have that, there's actually a removable discontinuity. So for that reason, there is a removable discontinuity at x equals 2. But that's not it. As it turns out, at 0, there is a jump discontinuity because we jump from this function to this part of the function to another part of the function. And then there is a, let me say, jump discontinuity at x equals 0. All right, cool. All right, so now we'll be discussing essentially motivation for a new tool that we can use to solve limits. All right, so here I have listed these 3 theorems. The first says if f and g are continuous at x equals a and c is a constant, and the following are also all continuous at x equals a. That's f plus g, f minus g, a constant times one of the functions, f times g and f divided by g, so long as the denominator evaluated at a is non-zero. Now these, of course, are all basically true because of the first 5 limit laws, and why that kind of connects to continuity is that the definition we saw for being continuous at x equals a is based on limits. It was that f of x, the limit as x goes to a of f of x, was equal to f of a. So that combined with limit laws actually says that these combinations of functions and constants are actually also continuous at x equals a. Now this next theorem here basically discusses the following types of functions that are continuous at every number in their domain. Now that part in their domain is pretty key. Basically it tells you if you have a function that is a combination of these types of functions, all you need to do is find the domain of that function, and that'll tell you that it is continuous and on that set of numbers, on its domain. Now, the reason why these types of functions are kind of key is we'll be actually seeing these functions a lot in this course, and these are basically non-piecewise defined functions. So piecewise defined functions are where you have possible weird discontinuities. Here we have possible weird discontinuities as well, but jump discontinuities basically do not exist in nature, which sounds weird. What do I even mean by that? Well, these functions have names. So these types of functions are kind of more natural in some sense, whereas piecewise defined functions are kind of Frankenstein together. So that's why I say in nature, which, you know, that's kind of maybe a little too figurative, but that's fine. So here are the functions, let me read them off. They're polynomial functions, rational functions, root functions, so any radical of any function, trigonometric functions, inverse trig functions, so like arcsine, arctangent, or if you don't like the arc notation, you can use tangent inverse, for instance, instead of arctangent. Exponentials, so e to the x, 2 to the 3x, something like that, or 2 to the x. Logarithmic, so log based 5 of x, ln of x. All of those functions are continuous in their domain, for every number in their domain. There's no jump discontinuity. There may be a removable discontinuity, but they're still continuous for all numbers in their domain. Perfect. So now this last theorem here is pretty important. It kind of connects things to limits. And this will actually basically finish off everything that we have to use as far as our understanding of limits go, and we'll be able to actually discuss and actually solve any type of limit problem with this last missing piece of the puzzle. And it says if f is continuous at b, where b is the limit as x goes to a of g of x, then the limit as x goes to a of f of g of x is f of the limit as x goes to a of g of x. What this basically means is we can pass the limit through continuous functions, so long as the function is continuous at that limit value. Otherwise, you can't actually evaluate that thing. And in this case, if this is just b, then the answer would be f of b. All right. So now we're going to take a look at some examples of these three. All right, so now for these examples, we're asked to do a series of different things, which are basically examples from the previous three theorems. So here we want to find out where this function is continuous. Now remember that this function is the quotient of two functions, and well, that's only when the denominator is non-zero, so we'll kind of consider that in a second. Also notice the numerator is the sum of two functions, each of which are, well, those types that we listed out. This is logarithmic, and this one is an inverse trig function. So these will actually each be continuous in their domain. So what are their domains? Well, as it turns out, tangent inverse actually has a domain of negative infinity to infinity, and that's because if you recall, tangent from negative pi over 2 to pi over 2 has asymptotes there, by the way. The graph of tangent looks like this in between negative pi over 2 and pi over 2. And if you swap the x and y axes, what you end up getting is a graph that looks something like this. And this is what we define the graph of tangent inverse to be, or otherwise known as arctangent. So that being said, its domain is continuous everywhere, and its domain specifically is negative infinity to infinity. What I should have said is it's continuous on that domain, which is kind of obvious, based on that theorem anyways. ln of x we saw actually has a graph that looks something like this. Let me kind of erase this for a moment. That's okay. And we saw that ln has a graph that looks like this. Its domain is basically from 0 to infinity, not including 0 because there is a vertical asymptote there. So the domain of the sum of these is restricted to the domain of the smaller one, which is 0 to infinity. So the domain of the top is from 0 to infinity. But notice that the denominator cannot be 0. And when is the denominator 0? So the denominator is 0 when x is either positive or negative 1. But notice negative 1 isn't even the domain, so all we need to get rid of is positive 1. So what that really tells us is that the domain of f of x is 0 to 1, open, union 1 to infinity. And again, the way I'm getting that is I'm going from 0 to the number we're removing, which is 1, and then continuing from the number to infinity. Which sounds funny because we're still at that number, but not really because these are open intervals. So we're not actually touching the number 1 itself. So I'm not even graphing this, but I'm just kind of reasoning out what the domain would be. And from that theorem we saw, a function is continuous on its domain. That's a combination of those functions we saw. So this function here is continuous wherever its domain is valid, wherever you can plug numbers into the function itself, which is here. So since this is the domain, then it's continuous on all numbers in this domain, namely these set of numbers here. All numbers from 0 to 1, or from 1 to infinity. Great. So now what? Now on to this one, we're asked to find this limit. Limit as x goes to pi of this. Now really what we want to strive for with limit problems again is DSP. But remember that we saw that DSP can really only be applied toward polynomial and rational functions, so long as you don't get a 0 denominator. But now we have somewhat of an understanding of, well, of limits of, in a sense of continuity, basically. So what am I trying to say there? Well, let's look at this function and ask ourselves, where is it continuous? So as it turns out, it's sine of x is a trig function, so that's continuous everywhere. Cosine is also a trig function, that's continuous everywhere as well. Everywhere in this domain, but the domain of sine and cosine are both negative infinity to infinity. The graph of sine, just to remind us, looks like this. And the graph of cosine is just a shift of that function. So they are indeed continuous in their domain, and their domains are negative infinity to infinity. So really all we need to do is find out where this is, where it has a zero denominator. But there's really good news there, because the only time the denominator will be 0 is if cosine will be negative 2, right? Because 2 minus 2 would give you 0. That should make sense. But you may think for a second, well, that can never happen, because notice cosine is bounded between negative 1 and 1. The lowest it can be is negative 1, the highest it can be is positive 1. So the fact that cosine is always bigger than or equal to negative 1 means it can't even be anywhere close to negative 2, so that this never has a 0 denominator. In fact, this is continuous everywhere. In particular, it's continuous at x equals pi. So if this function is continuous at pi, what does that mean? Well, remember that the definition of continuity at x equals a number means that the limit as x goes to that number of that function is equal to the function evaluated at that number. So what that really tells us is that really all we have to do is just plug that number into the function itself, which is something you probably thought, well, duh, just do that anyways. But continuity is really what allows us to do that. So the idea of continuity basically describes a generalization of the direct substitution property. And now notice sine of pi is 0, cosine of pi is negative 1. So this is 0 over 2 minus 1, which is 0 over 1, which is 0 anyways. Great. And now finally we'll use the last term we saw to evaluate this limit by passing this limit through the inverse sine function, which is continuous everywhere. Well, sine inverse is actually not continuous everywhere. The graph of sine inverse looks a little weird. Basically, it's only continuous from, let's just kind of take a look for a second. So remember that this is the graph of sine, and it's not 1 to 1, but if you break it up between negative pi over 2 and positive pi over 2, and look at this section only, and then you swap x and y axes, so like this is the x-axis and this is the y-axis. If you swap those, you actually get the graph of, I think it should look something like this. Yeah, so this is actually the graph of sine inverse of x. So notice that the range of sine was from negative 1 to 1, so that means the domain of sine inverse will also be from negative 1 to 1. So in fact, you could evaluate sine at negative 1. More importantly, we want to evaluate sine inverse. We can evaluate sine inverse at negative 1, I should say, even at positive 1. But notice we don't really care about what sine inverse of 1 or negative 1 is. We care what sine inverse of this expression is. So I'm just going to assume that it's continuous there, and I'm going to pass the limit through the function, the continuous function, and then we can evaluate the limit. But notice, if you just try to do that outright, you can't really do it. Because when you plug in 1, you get 1 minus 1 on top, because radical 1 is 1, and 1 minus 1 on the bottom as well, which is 0 over 0, which is an indeterminate function. Not function, but it's an indeterminate value, I should say. But notice we've actually seen limits that are of this form with a radical expression, and how we solve those is by multiplying top and bottom by the conjugate. So let's see. So the first thing I want to do is apply that theorem we saw, saying we can pass the limit through the continuous function. So now we have limit as x goes to 1 of this. But then we saw that to handle this type of limit that cannot be done by DSP, that involves a radical expression, we'll just multiply top and bottom, numerator and denominator, of that function by the conjugate 1 plus radical x. And that should hopefully get rid of the problem child, which is the denominator in this case. That's what gives us a 0 denominator after all. So I'm going to leave the denominator factored, as we've seen in those types of problems. But the numerator, I'm going to actually FOIL this out. Now notice this is a difference of squares, so the result will be 1 squared minus radical x squared, which is really just 1 minus x. because radical x squared is just x itself. So now we have the limit as x goes to 1 of that function now, and then we're taking sine inverse of that value. Now notice in this case, this is really nice because 1 minus x cancels with the expression 1 minus x, so we're left with 1 over 1 plus radical x. And hopefully that will give us some headway. Let's see. So we're still in the limit as x goes to 1 of 1 over 1 plus radical x now after cancellation. And now if we plug this in, this is just 1 plus radical 1 in the denominator, which is 1 plus 1, which is 2. So this really is the sine inverse function of 1 over 2. And I know that sine of pi over 6 is 1/2, so sine inverse of 1/2 must be pi over 6. Perfect. And of course you can plug in numbers that are close to 1 on either side of 1 into this, and you'll see that it'll be about pi over 6 on each side. Great. So now we're going to move on finally to the last thing we need to discuss in this section, which regards what is something called the intermediate value theorem. And what that basically entails is how we can calculate zeros of a function, and in specific we can actually solve any equation, but it's not as nice as it sounds. So let's take a look at what that's all about right now. Right, so now finally we have the intermediate value theorem, or for short IVT, and it basically says that if f is continuous on a closed interval and there's some number in between f of each of those endpoints of the interval, then there exists a number c in the open interval a to b such that f of c is equal to n. Now what exactly does that mean? Well, basically it says this, and you can visualize it based on, well, the following. So we have two x values a and b, and we have some continuous function, at least continuous between a and b in the closed interval. So it could be discontinuous outside of the interval for all we know. And if you take a look at f of b and f of a, by the way, I realized that this is technically incorrect to some extent. For all we know, f of a could be bigger than f of b if it's kind of like decreasing in that region. So let me write or the other way around, just kind of depending which one's larger. So I really should have said n is in between f of a and f of b, but that's fine. So if you pick some n value here that's somewhere in between them, then notice that the fact that f of x is continuous in between a and b, then this must hit the function somewhere. If it didn't, then there would be a breaking point. I mean, how else can you go from here to here without passing through this dotted line at n? There's no way to go around that, because since it's a function, it has to pass the vertical line test, and since it's continuous, it has to go through this path from a to b continuously. So it must pass through this dotted line somewhere, and the x value it corresponds to must be some value in between a and b, and in other words, that means n is equal to f of c. So that's really all it's saying from a graphing perspective, and we can actually use this idea to solve functions. Really, we can solve, not functions, but we can solve any equation really by treating it as a function. Now how we can treat an equation as a function is by solving for 0, essentially. So we can, for instance, this example here, we're going to move everything on one side so the 0's on the other, and we're going to actually find the 0 of that equation. So in particular, we're going to use a special instance of this where n is equal to 0. So I'll show that right now, and in fact I'll basically redraw this image here, but with this particular one in mind, and we'll go from there. Okay. So now, again, in particular, this example, we want to show that sine of x is equal to x squared minus x has a root in the open interval 1 to 2. Now, what the word root means is just solution. So I want to show there's a solution of this equation in this open interval. And how we can do that is by means of the interval, but by means of the intermediate value theorem. So we're going to consider f of x to be sine of x minus x squared plus x. So notice really what we want to show is that f of x has a 0. In other words, that this function is equal to 0 because that's equivalent to this equation here. So we basically want our n value to be 0 here, and we're going to kind of see what happens. But we have this interval to worry about. Now, I don't exactly know what this function looks like. Something I really want to do, to be quite honest, is to graph based on how each of these look. I think that's not too bad. Let's just try that. So sine of x looks like this. We've seen that already. And let's see. So in particular, sine actually, let me see, we're going from 1 to 2. So it's a little hard to translate because we have pi values here. So it's pi over 2. This is pi. That's actually not too bad because the pi is 3.14 and we're going from 1 to 2. So 1 and 2 are somewhere in between here. So the function will look, because pi over 2 is 1.5 something. So let's just say this is 1 and this is 2. Great. But at the same time, we're considering the graph of x squared minus x. So the graph of x squared minus x is a parabola. X squared minus x, by the way, is equal to 0. If you factor, you get x times x minus 1, which implies that the zeros are x equals 0 and positive 1 by essentially the zero factor property or zero product property, setting each part of this product equal to 0. Great. So what that tells me is that passing through 0 and passing through 1 and creating an upward parabola, that'll be the graph of x squared minus x. Now again, we're going from 1 to 2 is really what we care about. So we're looking at this line here. So I'm going to actually draw that at the same time. So it starts at 1 and then it goes up to, let's see, when we plug 2 into x squared minus x, you get 4 minus 2, which is 2. So the y value of this point would be 2. So this is 1 and it's highest for sine. And then let's just say 2 is a little bit higher like here. So we have this part of the parabola. Perfect. So this is kind of what we're looking at. We're looking basically at the intersecting point. So notice where these two intersect is indeed the solution to the equation. Now what I'm going to be doing actually is looking at the graph of this. Now it's going to be hard to graph f of x, but based on what we've discussed here as far as how these two behave, we can kind of see which one is on top and which one is on the bottom. So in other words, if we're doing sine minus this thing, we're going to have top minus bottom. So since here the top is going to be larger than the bottom, well, it sounds kind of weird, we're doing sine minus the parabola. But in between this red point, sine is on top. So we're going to have a positive difference there. Meaning if we were to graph f of x, there's some point where they intersect, let's call it C, I guess. And it's actually going to be above the x-axis because sine is bigger than x squared minus x there. So it will look something like this maybe. And then notice here, the parabola is going to be larger, but since we're doing sine minus the parabola, then that'll be below the x-axis. So something like this. So what we want to do essentially is hone in on this point, or this x value c. We want to find out what c is. Well, not really. We just want to show that c exists. Now you may argue, well, I graphed it already and we showed that there's a root in between 1 and 2, so that's really it, isn't it? Kind of, but if we had the graph at our disposal, then we're kind of done. But without graphing, what you can do is you can plug 1 and 2 into f of x, and you'll basically get these values here. So if you plug 1, what's f of 1? F of 1 is sine of 1 minus 1 squared plus 1. So this part here cancels out to 0, so really this is just whatever sine of 1 is. Now when you calculate sine of 1 using your calculator, you have to make sure first that you're in radians mode. Because we're not plugging in 1 degree, we're plugging in the number 1, which is 1 radian basically. So sine of 1 is about 0.84, 0.841 if you want to round to 3 decimal places. And similarly, you want to plug in the other endpoint, which is f of 2. So notice first off, f of 1 is indeed above the x-axis, and it's 0.841. And we kind of have the suspicion that f of 2 will be below the x-axis and should be negative. So when you plug in 2 here, well, notice you're going to get sine of 2 minus 2 squared, which is 4, plus 2. So negative 4 plus 2 is negative 2, so it's sine of 2 minus 2. Now sine of 2 radians is 0.909, and then that minus 2 will give you negative 0.109, and that rounds up to 091. So negative 0.9091. Let me say that again. Negative 1.091, sorry. There we go, that sounds good. And notice it is indeed negative, and of course this image is not to scale. Perfect. So now what? Well, now we're actually done, because notice, any value that's in between these two, there will exist an x value such that f of that x value is equal to any number in between them. And in particular, 0 is in the open interval 0.841 to negative, well, I guess it's the other way around, isn't it? To negative 0.091 to 0.841. There we go. So 0 is in that interval. That's not quite coming out on the screen. Let me kind of move things a little bit. Looks a little better. So 0 is indeed in between those. So that's our n in this case. And by the intermediate value theorem, so IVT implies that there is a number c such that f of c is equal to 0. Hence, that's our root in the open interval 1 to 2. So something I'm leaving out here is that c is in by the intermediate value theorem. So when we say c in the interval 1 to 2. So that's the part I'm kind of leaving out. So we've basically proven that there is a root of f of x in between the numbers 1 and 2. That, well, not a root, but there's a 0 of f of x in the interval 1 to 2, meaning that this equation actually has a solution in between 1 and 2. So I know I discussed this kind of visually first, just to give us an idea of what the intermediate value theorem really does for us. Now, exactly how you can find out what that number is, well, it's not actually too bad. Basically, what you can do is you can squeeze things in. So you can actually find out where this starts to become positive just by plugging in numbers. So if you guess that, let's say, it's halfway in between and you want to plug in 1.5, you can plug in 1.5 into f of x. All right, so I kind of wanted to show basically how you can use the intermediate value theorem to actually find the root of an equation, or a solution of an equation, in other words. But again, like I mentioned previously, it's not as nice as you may think. Basically, we're just plugging in numbers around where we think it is, and then kind of honing in more and more closer to it one at a time. Essentially, it's a lot of calculator work. So here, well, remember we had 1 to 2. F of 1 was a positive number, f of 2 was a negative number, so we ended up with a graph that looks something like that. F of 1 is some positive number, f of 2 is then some negative number. Not to scale, of course. And we found out that because it's continuous on the interval 1 to 2, because this is a continuous function, then there must exist some point in between 1 and 2, some x value between 1 and 2, that has f of that number in between 1 and 2 that'll give you 0, because f of 1 is positive and f of 2 is negative, and 0 is in between positive and negative numbers. But now if you actually were to decrease this interval from, instead of 1 to 2, 1.5 to 2 also works, because when you plug in 1.5 into f, you get also a positive number. So that means there's a solution in between 1.5 and 2. You can continue this until you basically get closer and closer and closer to the point. So I'm going to plug in numbers that are closer and closer to 2 until I get a negative, and then backtrack a bit. So I increase 1.5 to 1.6. It's also positive. Then I tried 1.61. It was also positive. I actually tried 1.7. Didn't work. 1.7 is too big. In other words, 1.7 is actually to the left of the point, and you can tell because f of 1.7 will result in a negative value. So there's that. And 1.61 is positive, so that's good. then 1 point, not a 0 point, that's just 1 point, sorry. So then 1.617 will also result in a positive number. 1.618 actually results in a negative number, but the actual solution to this rounds to 1.618. And that's because 1.615, I believe, is the last number that will result in positive up to 4 decimal places of accuracy. So rounding to 3 decimal places of accuracy, this solution here, so let me say x is approximately 1.618 after rounding, is the root of this function, not function, but this equation, meaning it's a 0 of this function. I'm kind of getting the word root and 0 mixed up, but that's fine. So regardless, again, we use the intermediate value theorem to come out with this number, and that's just by squeezing the initial given open interval to find the number in between. And very often, this is something you do in mathematics to find a solution to an equation. For instance, if you want to find the solution of a polynomial, where a polynomial is 0, polynomial equation, you can do so by plugging in numbers where you get one result positive, one result negative, since polynomials are continuous everywhere, and there's somewhere in between where it must pass through the x-axis, and you just kind of start looking closer and closer in, much like we did here. The only issue is, where do you even begin to start? So that is a question that goes beyond what we're trying to discuss here. But anyways, I think that's enough for the video. 2.5, the discussion has been kind of large, but it's a great discussion. You can kind of see how continuity is this kind of underlying idea that is essentially a foundation to limits amongst other things, even solving equations, something as simple as that. All right, so now we're going to move on to 2.6, which will discuss limits at infinity, which are not quite infinite limits. It's where we're going to be taking a look at limits where x approaches infinity or even negative infinity. And from there, we'll just continue on to chapter 2. And hope you enjoyed this video. See you in the next videos for 2.6 and beyond. Thanks for watching. See you then.